All right, this session we're going to do operation of very old radios. Okay, I have here a radio that was similar to what would be used in 1920, and even earlier. It probably could be even 1915. It would be a homemade radio. This one is homemade. I made it about 10 years ago. Okay, if we look at it, we have a tuning coil. We have the tuning condenser. Notice that the tuning condenser uses square plates. This was because you couldn't go to the store and buy these tuning condensers yet. They had not yet made the nice decent quality ones and put them on sale. They had people that had them. The military and stuff like that had them. But they were not yet in the Duck catalog and the other radio sources. Okay, then we have the grid leak and the grid bypass condenser. Both of these are homemade. The condenser is made by having two layers of aluminum foil separated by plastic tape. In the past it would have been paper, but I just used plastic tape because nobody's going to know any different. Now, the grid leak resistor is this piece of rod here. It's a piece of wood, and pencil was scraped onto it to put a carbon coating, and then some wire wrapped around the edges to get contact. And the total resistance of this is about 3 megohms for the grid leak. And that is connected to the grid wire of the Audion. Okay? The bypass condenser for the headphones is made in the same way. A piece of wood dowel has aluminum foil and tape forming a capacitor of about 2,000 picofarads, and that bypasses the headphones for the RF that may feed through the Audion. Now, the Audion is one of my homemade spherical Audion tubes. This is a double wing spherical Audion, and it provides the gain for the radio. Now, normally a set of headphones would be used to go ahead and operate the radio, but we can't demonstrate that on the camera. So what I've done is I've gone ahead and hooked up a speaker and a little audio amplifier, solid-state audio amplifier, that'll take the radio signal and boost it up to where we can hear it in the speaker. Now, to couple to the speaker, we can't just hook the output of the radio to it. The output of the radio is about 68 volts that goes across to high impedance headphones. The headphones that we use are high impedance type. These have a DC resistance of about 2,000 ohms, and that provides the plate load for the Audion. Okay, to simulate that so we can couple to the audio amplifier, I've just used a coupling transformer. This is a 1:5 ratio coupling transformer. So the plate goes onto the plate windings and the amplifier goes to the grid windings of the transformer. This one is from back in the 20s. It's an old coupling transformer. And that just goes over and gets fed into the input of the amplifier. And the output of the amplifier goes to the speaker. Okay, it's kind of Mickey Mouse setup, but that's the only way we can get the signal into the speaker to where we can actually hear it. Now, let's see how this thing works. Okay, we've got the power supply. We've got the B plus at 68 volts, and the filament voltage is set at 2 volts. And that gives us a little bit of range. The maximum voltage we ever want to put on this Audion is 2 volts. If we go past that, we start straining the filament, and we could potentially burn it out. So we set it at a maximum of 2 volts, and that gives our rheostat so that we can adjust it to a proper value. The normal operating voltage is somewhere around 1.2 to 1.3 volts. Okay, we'll bring the voltage up. Now, notice how we hear several stations at once. By adjusting the coupling, see, when we adjust the coupling just right, we can clearly separate those two stations that were coming in on each other. And by adjusting the gain a little bit, we can make it to where they're two very separate stations. There's one, and there's the other. Notice how little the capacitor moves. And yet we're able to clearly separate it. That's a single tune circuit separating those stations. Now, for an antenna, we have an outside antenna, and it's about 25 feet long. It's up under the eaves of the house. So we can see that an old radio like this, using an Audion tube that is very primitive. It has a gain of about, a transconductance of about 100 to 200. It's between 100 and 200, which is very low compared to any of the modern tubes. It still gives excellent performance, partly because we have very strong radio stations. Okay, that is this particular radio. It's typical of what you would see back in 1920 from a homemade radio that some fellow would make in his shop or garage or even on the kitchen table, using available parts and bits and pieces of metal and whatever, and an Audion tube that cost him about a week's salary. Okay, next we're going to go ahead and we're going to look at, let's look at the circuit of it first. Okay, this is the circuit of that particular radio. Okay, we have the input variable coupler. We have the moving coil, which couples the antenna onto the tune circuit. And by coupling it very tightly, we could get a lot more gain. And by backing the coupling off, we lose some gain, but we get selectivity. The tuning condenser selects the frequency it's tuned to. Okay, we have the grid leak and the grid capacitor, which are connected through to the grid of the Audion. The rheostat for the filament is in the filament circuit, and that takes our 2 volts and drops it down to whatever we need to operate the Audion. Now, the Audion is pretty critical to filament emission, so we have to have that control. We can't just plug it in. You know, modern tubes are very carefully designed to where the emission is not controlled by the filament voltage. You heat the filament up and it has a constant emission, and all the gain of the tube is controlled by varying the grid bias. And this is completely different than the way these primitive Audion tubes worked. They work to adjust the transconductance entirely by adjusting the filament emission. And that was kind of a shaky thing, but due to the extreme variation in the tubes, you couldn't get 2 tubes that were the same emission for the same voltage. So they had to have an adjustment on there. And you look at all these old radios, and they all had a filament rheostat because the tubes weren't equal enough in manufacture to where you could use a constant filament voltage. Okay, now our 2000 picofarad capacitor from the plate to ground takes any RF that happens to leak through the Audion, and that just bypasses it, and it gives you a clean audio frequency on the headphones. And the headphones connect to here, and that provides the DC path for the tube. Okay, the B plus is fairly high on these Audions. These are Audions that I'm making are high vacuum Audions, so they use higher B plus than the old gas Audions. The gas Audions would use 22 volts or so on it. But for the high vacuum ones, the higher the voltage, the better. You get better signal with the higher voltage. So we're using 67 volts on it, which gives a very good sharp characteristic curve, so we get good detection and amplification. Okay, and then we have a 10 microfarad capacitor from B plus to the common, so that we have a very steady B plus here, no RF or audio signal on it. Okay, that's all there is in this old antique radio. So you can see it doesn't take much to build one of those. The biggest problem is finding the antique parts. I mean, you can use modern parts, build the thing with modern tube and things like that, and it would work just fine, with the exception of the rheostat. You'd have to have a certain type of tube to make one of these radios, using a modern tube that would vary the gain with the filament. You'd use something like one of the battery radio tubes from the 1930s, and those have a filament cathode, and their emission is easily controlled with a filament. I mean, with a filament rheostat. Okay, that is that radio. Okay, now, this is one of the earliest radios that there is. It is a loose coupler radio. They call it a loose coupler because you have a big coil inside of here, and you have a loose one that slides in and out that changes the coupling. So if you have it coupled way in, you get a lot of gain, but your selectivity decreases. And if you move it out, you get more selectivity, but your signal level drops because you're transferring less energy between the two coils. Now this is called a Navy loose coupler. Navy. I mean, it was made for the Navy, and the reason it's called the Navy type is because the Navy did not like the slider type. They originally had sliders that would slide across the coil. Well, they didn't like that because they were erratic. So the Navy said, okay, take it and make it to where you have taps on the coil and a switch to go to the taps. So instead of sliding a slider to select your position on the coil, the Navy type, you use a switch and it selects different taps, and they have lots and lots and lots and lots of them. It makes it an extreme nuisance to build one, but these taps are repeatable. You could say, okay, give us a number 12 and a number 7, and that'll give you frequency number so-and-so. You could actually write down the setting of the switch and go back to that frequency again. Whereas with the slider type, it was kind of, okay, put it about an inch and a half from this end, and the other one about 2 inches from that end, and and that's about it. And there wasn't any real positive way to set the thing back to something, some setting. Now on the other one, on the other coil, we have another set. Same exact thing. We have a big rotary switch here with a lot of taps that go to the coil, and this allows you to set the coupling to change the frequency. Because if you have a whole lot of turns, then it has too much reactance for the upper frequency bands. So by setting it to a tap where you only use a small portion of the coil, then the inductance is smaller, so you match the higher frequencies better. The whole thing depended on the antenna itself for the capacitance. The main coil forms a series resonant circuit with the antenna being the capacitance and this coil being the inductor. And by adjusting the inductance, you can set the frequency. Due to the nature of antennas and the capacitance, they're very low Q. So the selectivity of these loose couplers is abysmal at best. Okay, to detect the signal, we use a crystal detector. And here we have our crystal detector. And what it is we have the crystal itself, which is in a little cup here with a set screw, and then we have a cat whisker, which is just a little piece of fine wire that you can adjust and get you a sensitive spot on the crystal. All right, let's go ahead. Normally these were used with headphones, standard high impedance headphones, and they would give depending on how good your headphones were, you could pick up the signals a little bit, sort of. I mean, there were, the crystal sets were definitely marginal at best. Okay, we've got our high-gain audio amplifier hooked up here to our speaker, so we'll have a little bit better results. Okay, now I've got the antenna connected onto it, and a ground, and that's to the series tune circuit inside of here, and we've got the crystal detector connected to here. It comes off the connections on the end. These two rods have spring wipers inside that connect this circuit onto these rods, and then the rods have wires going down through the inside, and they end up on these terminals here. And those terminals are connected to our crystal detector. Okay, we'll hook our amplifier, and we're picking something up. No way of knowing what station it is without just listening. Now, we can adjust the crystal. There we go, that's a pretty good spot right there. See, some parts of the crystal are not very sensitive and other parts don't detect at all. Oop. And the slightest touch ruins it. That's why they didn't like crystal sets, because vibration would cause them to get off of the sensitive spot and you'd have to readjust it. So if they were on a ship and the engine was vibrating the ship, the radio operator would be very pissed off, because he'd keep losing sensitivity because the vibration would knock the crystal off. Let's see. Yep. See, there's a spot, but it's not very sensitive. Now, to compare it, let me get a... okay, here we have some 1N34 diodes. These are old-fashioned ones, very old ones. And let me get one of these. I'll get one of the glass ones because I can hold it without getting my fingers all over it. Get you. Now, see, that's an old-fashioned 1N34 diode. And if I put that across there, we can see how it compares. Okay, now there's just with a standard diode across it. Now the crystal itself is not touching, and that's what the sensitivity we get using a standard diode. Okay, let's pull that off and see what we get if we try to adjust it. See, that's pretty low right there. There's some pretty hot spots. Okay. See, now that one's pretty close to being as sensitive as a modern diode. Okay, now, changing the frequency. But the selectivity is really lousy. We're getting two stations at once. Okay, we'll try. That's no good. See, this is going shorter, the smaller number of turns here. And we're at the upper end. This is the higher frequency end of the of the coil. So to receive that best, we've got it pushed in about halfway, and we've got this set at a smaller number of turns, so the inductance of this coil matches the higher frequencies better. But the selectivity is very poor because the Q of the antenna acting as a capacitor is very poor. Now, back in the old days, there were not too many stations. Sometimes there'd be more stations, but some of them would be very weak compared to the one that you wanted to listen to. So you could get away with having poor selectivity. You know, there we get good sensitivity, but we can't tell anything because all of the stations are coming in at once. It's very difficult to tune them in. Okay. Now there, we got, this is on the very low end, so we're getting about 610. This station is 610 on the broadcast band, and we're able to tune it pretty good. Because there's no other stations near it. But when we get up into the higher stations, this is about 950. It's almost impossible to separate them. So we can see that a loose coupler, while it works, it is not really a very good receiver. But that's how you make a loose coupler crystal set operate. You hook your antenna and ground onto it, and then you start playing with the connections. Now some of these will have sliders, and instead of moving a switch, you'll just be moving the slider on there to select the station. And all you're doing to select the station is you're changing the inductance and making it resonate with the capacitance of the antenna to resonate at the frequency you want to pick up. But since the antenna has such low Q, you know, you're not going to have very sharp tune circuit, you know, compared to this one that we demonstrated here, which was very sharp. All right, let's put this aside and go on to our next set, which is the DeForest Audion RJ4. All right, here we have a DeForest RJ4 Audion control box connected up as a radio. The RJ4 itself is not a radio. It was only an Audion control box. It was meant to supply B+ and the hookup, the basic connections for the Audion tube. This was made back in like 1910, somewhere around there, 1909, 1910, because nobody knew how to hook up an Audion tube. So DeForest came up with this simple little box here. There were several other versions of this. There was one that was a little bit earlier than this that wasn't quite as elaborate, and then there was this one. But the RJ4 is pretty much the earliest one that you're going to find. This one is reproduction. You know, getting an original, you're talking several $1,000s. But this one's an original. I mean, a copy of the original, and uses all the original parts and things like that. And I've got the homemade Audion tube in there. Now, to the output of the radio normally went to a set of headphones. I don't know what I did with them. Headphones are around here somewhere, but headphones, of course, are no good for on the video. You can't hear them on the video. So what we do is we take the telephone's output, where the headphones normally would connect, and we go to an audio transformer. This is an old-fashioned audio transformer from a 1930s radio, and we hook the high impedance part onto the DeForest RJ4, and we take the low impedance part and we connect it to our high gain transistorized anachronistic amplifier there, and then that goes to our horn speaker. So at least we're reasonably period. We're going to be more period in just a minute, but right now we're just going to show how the RJ4 works. Okay, we're using the same tuning mechanism that we used on the other radio. So what we do is we got power supply, and we've got our filament voltage set to 2 volts, which is the same as they would operate this at normally. They use a 2-volt storage battery cell and lead acid cell to operate the filament. And then the filament is adjusted using this rheostat on the side. On the back, we have the 2 terminals that are used for connecting to the tuner. And we just go from our tuner to the different connections back there. We have one for ground and one for the signal, one for ground signal, whichever. Okay, and then we got our antenna connected up to the tuner like we did before. Okay, there are 2 controls on the control box front. We have one of them on the side, which was used for gas Audion tubes. Back when this Audion box was made, the only tubes that were available, the only Audions, were gas Audions. DeForest and McClandis did not have vacuum pumps that were capable of pulling a high vacuum. So inherently, every tube they made was a gas Audion. They had on the order of 1 to 5 microns of gas pressure in them, of air. So the operation of the gas Audion is different than that of a high vacuum Audion. This is a high vacuum Audion, and it operates with any kind of B+ voltage at all. You can put the B+ voltage to any level you want, and it'll operate perfectly fine. Whereas with a gas Audion, the B+ voltage is extremely critical. You have to have it right at a point just before the gas ionizes. Because if the gas ionizes, it goes into conduction, and then you get no gain at all. And that's what this switch was for. Inside the box, inside the Audion box, there was a set of batteries to supply the B+ voltage for the Audion. And they had 4 4.5 volt batteries, and then they had another set of 4, I think there was 4 flashlight cells, 1.5 volt cells. So the lowest setting was 18 volts, and then you had 19.5, and then 21, and then 20, let's see, then 22.5, and then 23, 24. Okay, so those were the different voltages that you could select with your B+ switch. But this will not have any effect on a high vacuum Audion because the characteristics of the Audion are very, they just don't depend on the plate voltage that much. The filament voltage is what sets the gain of the high vacuum one. Now our other switch over here is simply turns the filament voltage on and off. That's just used to turn on the power to the filament. It has no other function. And then on the side we have our rheostat that sets the filament brightness, how much emission we get. All right, let's turn it on and see how it works. Okay, you see we have our filament lit up, and let's see, we tune. So that's basically how an RJ4 works. Now, an RJ4 works, but of course they would not have had this nice of an operation because we have 50,000 watt radio stations all over the place, plus the transistor amplifier, gain of about about 3,000 in that transistor amplifier. All right, let's shut this off, and let's go ahead and hook it up the way it would have been hooked up back in the 1920s to drive a horn speaker. To do that, we will use a DeForest amplifier. Wow, look at that. This, of course, is not an original. An original would cost you thousands and thousands of dollars. This is a copy, and we have our two fresh-made Audions, and it's an amplifier. Okay, so let's go ahead and we'll hook it up to the RJ4 and use it to drive the speaker. Okay, now here we have our setup. We have the RJ4 connected up exactly as before, and then we take the output of the RJ4 and we go into a coupling transformer, and we take the secondary of the coupling transformer and we connect it to the input of the amplifier. And this is a two-stage Audion amplifier. Each Audion has a gain of about 6, so it has a gain of about 36 times 3 is about 100. The transformer has a gain of 3, or maybe even 5. I think I used a 5 to 1 in here. So we would have 6 times 5 would be 30 times 6. Okay, almost 200. We'd have a gain of almost 200 out of this. Now that doesn't compare to the thousands gain that we have in this solid state amplifier, but still it's adequate. I mean, and this is what they had back in the old days. Now, this was also able to be connected as a radio, the same as the RJ4. You could connect the tune circuit straight to the input here, and it would detect and work as a detected radio with 2 stages, a detector stage and an amplifier stage. There are 2 terminals on the top here where you can hook your headphones, and by selecting here you could select which plate you would connect to your outputs. And then this is our filament control here for the filaments in the amplifier, and then we have the same B+ switch that is on the RJ4, but this one has got 1, 2, 3, 4, 5, 6, 7, 8. It's got 9 different voltages. And I took the voltage markings that they used on the original panel. It starts at 12 and goes up to 30-something volts. I mean, I just copied what was on the panel of the original. I don't know. I find it hard to imagine they were using 12 volts on the supply, but I guess that's what was on the original panel. I mean, I copied this directly. All of these labels and things are copied right off of an original unit. Okay, let's turn it on and we'll see how it works. Okay, first we turn on our RJ4 unit. Okay, and then this unit, I went ahead and cheated, and I built in a power supply. What I did was I took a box and I made it look like an old-fashioned battery, and inside of it is a power supply. So I don't have to hook up wires onto the main power supply like the RJ4. I have made RJ4s for sale that had a complete internal power supply, but this one here, I don't have any more of those internal power supplies built up, so this one I still have to hook up to the external supply. Okay, we just switched the switch on, and we now have the filaments, the Audions have lit up, and there we are. See, now this one, that's a weak station. And everything we got out of it, we can't get enough gain to really get good volume. Whereas on the solid state amplifier, we were able to blast the room with it. So that's how, back in the 1915 era, they were able to drive a speaker. They didn't have a lot of speakers back in 1915. This particular speaker is anachronistic. It's in the 20s. It came out in about 1924, something like that. And but there were horn speakers back in 1915. I think Western Electric made a couple of horn speakers back then. So you could actually have a horn speaker. So that is a radio that you would have from a long, long, long time ago. Glowing filaments right out in the open. You know, they got more modern. When they got up into the 20s, they started hiding the tubes inside to where you didn't see them. And you kind of lost that interesting glow. All right, that's it.